Okay, good morning, everyone. Let's get started with the second lecture of the mini course on dark matter, neutrino, and baryon asymmetry with Professor Debasish. So take your time. Thank you.
Okay, thank you. Okay, so I hope I'm audible to everyone. So, so today we'll talk about dark matter. So first, I'll start with some introduction, like how do we know that there is dark matter in the universe, although we can't see it directly. So we observe dark matter at different scales. Okay, so I'll start with the scale of the galaxy, which is the smallest scale we can think of. Galaxy. So what we look at, we find out the velocities of different objects in the galaxies as they are far away from the center, and try to fit it with the Newtonian gravity, and we find that there is a discrepancy. So this was actually pointed out by people like Oort, then Rubin, and so on. So we find the acceleration as v square by r. V is r the distance, so you can think of the galaxy like this. So there is a bulge, and there is a disk part, something like this, and you are looking at objects sitting here with different velocity profile at a distance from r. Okay, so this is the distance r. Okay, so if you're very close to the bulge, you can actually think of this as a spherical one. So you can actually find out the mass at any r is 4 by 3 pi r cube, if you are talking about the spherical bulge. And that you can actually compare, because this you also know from the Newtonian gravity, gm by r. Okay, so this mass is the mass which is actually confined within the radius r. So if you find it out, you will find that a will actually, sorry, not a, the v, you will find if you actually equate it, you will find that v will grow as r in the, if you are in this part, okay, inside the galaxy. But if you go far away, m is no longer a function of r. M is actually constant if you are here. Of course, there will be a difference if in the disk region, which I'm not going to consider because that will be a bit complicated. But for the bulge, it is very simple. If you are very far away, the whole mass is actually confined. It is not actually a function of radius. So then you will find that your m is actually constant, and instead of v is actually going as 1 by root r. Okay. So this, if you plot velocity as a function of r, you should find that it actually grows initially like this. And then, of course, there will be something here because I'm not taking this part into account properly. But at the far away, you expect it should actually fall down as 1 by root r. But so this is your Newtonian gravity. But what we have seen experimentally is that it remains more or less flat. Okay, so these are called galaxy rotation curves. And it actually tells you that if you believe that your Newtonian or Einstein's theory of gravity is correct one, it goes as 1 by r square force, then it tells you that there should be more mass compared to the mass that you see in the visible stars as well as the gas that you have in the galaxies. Okay, so that tells you that there should be more matter compared to what you see in the stars and ordinary baryons and so on and so forth. Okay, so this is one of the primary evidence that there should be dark matter. Okay, and if you go to bigger scales, for example, you can go to clusters. That was pointed out long back by Zwicky. So in the cluster is actually a composition of different stars. So there also you can find out the velocity of the stars, and then you find that the velocities are actually too large, okay, which could be binded within that group of stars or that cluster by the gravitational potential, which is coming only from the visible stars as well as the intra-cluster gas, okay. So if it is moving very fast, you want to keep that in the same orbit or a group of the same cluster. That means you need more mass to put into that cluster. Otherwise, it will go away, okay, because it's moving very fast. So that actually tells you. So for example, if you look at the coma cluster, by looking at the velocities of the stars inside the coma cluster, you can make an estimate because you know the virial theorem, which tells you that your kinetic energy is minus of the potential energy divided by 2. So if you find out the velocity, which tells you the kinetic energy, you can find out what should be the mass inside the cluster. Okay, so this tells you that mass of the coma cluster should be of the order of 2 into 10 to the power 15 solar mass. On the other hand, if you compute the mass by looking at the stars as well as the intracluster gas, you will find that that will contribute only around 10 to 20%. Okay, so most of the mass of the coma cluster, if you want to keep the clusters stars in the cluster moving with so high velocities, they have to be more mass compared to what you see coming from the baryons, gas, or the stars. Okay, so that means that you not only the galactic scale, even the cluster scales also, you have to have more mass compared to what you see in your ordinary telescopes, okay? In the electromagnetic spectrum, for example. So this also tells you that there should be more mass at the cluster scales, okay? And more mass at the galactic scale. You can also talk about other evidence, for example, gravitational lensing. So you can see, you can have lensing. So, for example, one very robust proof of dark matter is the bullet cluster, which is a collision of two clusters and they actually go through each other. So, if two guys are coming and they collide, so you can have some, these are like, you can say this is your visible, this is your visible, let us say. And when they go through each other, you find that the visible part, they get dragged because they interact with each other a lot because of electromagnetic and other interactions. But the dark matter part, they actually goes, they go through each other as if they don't see each other. Okay, and how do you know that this has happened? Because you don't see it directly, you see only this in your x-ray or whatever electromagnetic telescope you have, but you can do a gravitational lensing of this whole thing because you have a, so this acts like a foreground to the background stars and all. Okay, so you can look at the stars, light coming from the background stars, and there you see that there's more banding here. You see all these Einstein rings forming because more in this region, more in this region, less in this region, and this region you anyway see with your ordinary telescopes. And this actually tells you that this actually tells you two things, which is important. One is that obviously there is dark matter. Most of the mass is confined in the dark matter. The second thing is that the dark matter is collisionless. That means they don't interact with each other. They just go through each other. Okay, so this tells you that dark matter should be very different from baryons because baryon, they don't pass through each other. They see each other because of electromagnetic strong and all other interactions, right? So this is another evidence. Then you can also look at much bigger scale, the scale of cosmology. So for example, if you look at CMB, this is D. So CMB, you know that the CMB was formed when the proton and the electron, they form hydrogen. And after that, the photons, which are there in the universe, they actually free streaming. Okay, so those are the photons we see now. And in principle, they should have, if we start with FLRW universe, in principle, they should have the same temperature coming from all directions. But we know that our universe is not a perfectly homogeneous and isotropic. It has some small perturbations. That's why we exist today. So if you try to measure those things, so it actually, you find out those things as a small anisotropies or small difference or temperature fluctuations in the blackbody spectrum of the photons coming from the recombination era. So this happens at time of the order of 380,000 years. So if we look at these guys now, these photons now, it actually gives us a picture of the universe as early as 380,000 years. Okay, and now we know that we live in a universe which is 14 billion years old. So this you can actually, so this T is the mean temperature of the photon right now is 2.73 Kelvin. It is actually redshifting because it has traveled a long distance from 380,000 years to 14 billion years. And this actually tells you that there is small fluctuations and that you can actually write down as a Fourier, the spherical harmonics, and that is given by this YLM. And this quantity we actually write in a more convenient form as Cl12 plus 1 ELM. Okay, so this is effectively you parameterize your temperature fluctuations in terms of this quantity, which you will see in most of the CMB plots of power spectrum. So CL and L, and you'll find that it goes like this, then there's a this one, then there's a third peak, then there are many other peaks, and it goes like this. Okay, and the first peak, it comes around L approximately 200. And if you go to higher L's, it means you are talking about smaller and smaller scales, because L is like the wave number. Wave number is 1 by length scales. So the first peak, location of the first peak tells you that you live in a spatially flat universe. And the combination of first, second, and third. So these peaks are coming because there is something like dark matter is there, and it actually acts like a gravitational potential well. And you have the baryons and the photons, and they are oscillating. Okay, so you have like compression, rarefaction, compression, rarefaction. So you can think of this as a compression, and this you think as a rarefaction, and then you can think as a compression. Okay, so all these things, it's more complicated than the way I'm saying, but it's the first three peaks actually tells you very robustly what is the nature of our universe, what it actually contains right now. It tells you that we live in a spatially flat universe, k equal to 0, and the height and the positions of these peaks, it actually tells you how much of matter should be there in the universe, how much of dark matter should be there in the universe. So if, for example, if you put more baryon, these peaks will go up, okay? Because you will see more structures, okay, than what we see. So this is another one, and the last one is actually from the structure formation itself. As you know that if we always live in a homogeneous and isotropic universe, structures cannot form, because structures actually tell you that the universe is not homogeneous and isotropic. So you need some seeds of those structure formation, and those seeds are actually included in this anisotropies. You can relate those two things. And if you start with those seeds, what happens is that since dark matter does not interact as strongly as the electromagnetic as the baryons, and dark matter is supposed to be a bit heavy and cold and non-relativistic. So you can expect that the dark matter, since it is large in amount, it will be more clumpy compared to baryons. And if it is more clumpy, it will act like a potential well, and the baryons will fall into that potential well and form structures. And for that to happen, dark matter should be non-relativistic. It should not be relativistic, at least at the time of recombination, because after that, we know that the structures are forming much rapidly, right? So those things you can actually find out in something called the matter power spectrum. So this is actually is denoted as delta K square, and delta X T. This is basically your rho X T divided by rho 0. If you always live in a homogeneous and isotropic universe, rho is same as the rho average. Okay, it's 1. But it's not 1, because rho at different x will be different, right? So that's why if you plot it, and this delta k is just a Fourier transform of this, okay? And you plot it as a function of k. So once again, if you talk about small k, you talk about large scales. If you talk about large k, you talk about small scales, okay? So if you plot this, you don't get a horizontal flat line. You actually get something like this. Okay, you don't get structures beyond a particular point, right? You don't see structures here. You see the structures at the galactic scale, for example, right? So that's why it falls here. And this data is coming from the CMB, because CMB always gives you a picture of the large universe, like of the horizon size. And these are coming from the galactic surveys at smaller scales, because they look at how much of gas is there at smaller scales, like of kiloparsec and so on. So they come from, say, the Sloan Digital Sky Survey, or you can have Lyman alpha, right? So this actually is very consistent with non-relativistic or cold dark matter. For example, if you have neutrinos as dark matter, what will happen is that at this scale, it will look similar, but if you go to small scales, it will actually erase the structures. So this is basically for your hot dark matter, which is neutrinos, right? So this actually tells you, and this is another reason I mentioned yesterday, how do you constrain neutrino mass, for example? How cosmology can tell you what should be the bound on the neutrino mass. Because if you give more neutrino mass, you mean you are giving more energy to the neutrinos, and neutrinos are hot. Neutrinos are relativistic. So that means you are compensating from you're taking some part of the total dark matter, giving more into the hot part compared to the cold part. So it will try to erase structures at small scales. Okay, so from that, since you don't see this erasing of structures at low scale, because you see structures at the solar system level, at the galaxy level, so from that you can constrain how much of dark matter should be there and how much of it can be hot dark matter. Okay, yes. Delta K is a Fourier transform of this. This is the average density. Mean density, yeah. No, this is about the size of the scales, right? K is 2 pi by lambda. So lambda tells you the size. So you have you have big structures, but you cannot have structures beyond a particular scale, right? So below the scale of the solar system, there's no structures. Yeah. So that's the reason it falls. Yeah. Is it okay? Okay, good. Okay, we can discuss it maybe after the class. Okay. Okay, so I will not spend much time on the evidence. I'll go to the question, which is more important to us. I think we all are convinced beyond any doubt that there is dark matter in the universe. And now the next question we want to ask, which is more important, what is dark matter? Okay, so let's go there. Before that, before go to what is dark matter, we should ask from these slides, this expression, that what should be the nature of dark matter. First thing is that since we call it dark already, that it should not have any electromagnetic interactions. Okay, it should be neutral. So it should be EM or color neutral. It should be stable or long-lived enough, right? And it should give rise to the observed. For example, I forgot to mention that CMB tells you that right now it gives you a pie chart of the dark matter and the other matter. So you find that dark matter. So this is your dark matter, which is 26%, and this is your baryon, which is around 5% or maybe 6%, and the rest of it is dark energy, which is 68%. Okay, so we have to have some kind of dark matter which not only satisfies this, but it also should give rise to 26% in the present universe. Okay, so that is what we have to check. Now, what is the closest particle that we can have? We can think of, without really thinking about beyond standard model, in the standard model itself, there's one particle at least which will satisfy some of the criteria, which is neutrinos, right? Neutrinos are light, stable, they have mass, we know, we have seen in the last lecture. Now we can ask the question that can neutrinos be dark matter? And we don't have to go to beyond standard model. But there are three problems. The problem number one, neutrinos, if you calculate the number density of neutrinos, is very simple because it's always relativistic. So you can find out just from the equilibrium distributions, you know that you can use the Fermi-Dirac and you can find out the number density, Z by 2 pi cube Fp dqp. You can find it out and you can just find out at the present temperature, and you will find that number density of neutrino right now is at the order of 335 cm in a cube, and mass of neutrinos is of the order of 0.1 electron volt. So you can find out what is the number density, what is the energy density of neutrino, and that you can find just by mass of neutrino multiplied by number density. This you can do because neutrinos right now are non-relativistic. Okay, so any non-relativistic guy, you find out the energy density just like this. So if you find it out, you find that omega nu is the energy density of neutrinos divided by the critical density, and you find that this comes out to be of less than 2.8. If you use this as a upper bound on neutrino mass, it comes out to be 2.8 into 10 to the minus 3, which is very small compared to omega dark matter. Omega dark matter should be 0.26. Okay, so it cannot be. Second reason, any fermion dark matter mass should be more than or the order of keV. Why? This comes from the phase space constraints, completely model independent. Your galaxy has a phase space, right? Galaxy has a volume. You can find out the velocity distribution of the particles, so it has a finite phase space. So the phase space occupied by a fermion dark matter cannot be more than a degenerate Fermi gas, right? Because Fermi exclusion principle prevents you from putting more fermions than what the phase space allows, right? So this is called the Tremaine gun bound. This is very robust. You cannot play with this bound at all because it is completely model independent. So this actually rules out that neutrinos, because it's a fermion and its mass is so small compared to the bound that you get from the phase space arguments, neutrinos cannot be dark matter. Third reason, neutrinos are hot. They are relativistic at the time of recombination. Okay, so they will not allow structure formation. And in more quantifiable way, you talk about these things as something called free streaming length. It's like how much distance neutrinos can travel without interacting with something else. And that comes out to be very large, of the order of megaparsec. But we see structures at the kiloparsec level or even below, like solar system, like the Milky Way. So neutrinos will not allow structure formation at small scales. This is the reason why this plot makes sense. It will allow at large scales, but it will not allow here. Okay, so all these three reasons convince that neutrinos are not dark matter. Okay, so then we should have something else. Okay, so let's see. So then what should be the dark matter? You talk about any particle, but if you talk about any particle which satisfies those criteria, you have to calculate the dark matter abundance. Okay, now there are so many different ways of calculating dark matter abundance. So one is the something called WIMP. Is probably one of the most popular dark matter. So it actually introduces a particle which is heavy enough and it has some interactions apart from gravity. For example, all these evidences, we should note that these evidences are based on purely gravitational interaction. It does not tell you anything that dark matter should have some interactions apart from gravity. Okay, so WIMP is still a hypothesis because it actually assumes that dark matter has some other interactions also, which actually helps to produce that particle in equilibrium in the early universe. Okay, so if you do it, so one has to keep in mind that if we want to find out the number density, the number density is proportional to the temperature. If T is number density is proportional to T cube, is T is much more than M, and the number density is proportional to mt 3 by 2 e to the power minus m by t. And this you can find out just from the uh, formula that I wrote. That formula I wrote for the number density. You use Fp is equal to either Bose-Einstein or Fermi-Dirac. You will get these relations. Okay. So if a particle is always in equilibrium, as I said, WIMP will be produced in equilibrium. What will happen is that at late temperature, as the temperature is going down because the universe is expanding, you can find that it will become almost negligible because of this exponential suppression. Am I audible? Okay, great. Okay, so we need to take it out of equilibrium at some point, and that's called the freeze out. Okay, so how to look at this number? So for example, this guy is produced, so we have to find out its number or the abundance by solving something called Boltzmann equation. Okay, so I'll talk about a very intuitive way of writing down the Boltzmann equations. I will not go to the very rigorous way of writing the Boltzmann equation due to lack of time. If you want to look at the more rigorous way, you can look at the Kolben-Turner, the early universe. All my discussions is actually based on that book, but I will give you a more intuitive way. For example, if you say that the number of this guy dark matter, let's say I denote it as chi. What we are interested is that if this guy is produced in equilibrium, I know its number density, but I know that it is going to change because it's going out of equilibrium. So I have to solve the Boltzmann equation. Otherwise, I cannot find it out. If it is always in equilibrium, my number density is just this. It's very simple. Okay. If it is not in equilibrium, I cannot use equilibrium distribution functions to find out the number density. So now I want to find out, I want to solve this equation, which will tell me how much of dark matter particles should be there in the present universe. So this is number divided by time. What it should be? It should be the rate at which standard model particle is going to produce chi. Okay, that will give you the plus contribution. Second is the rate at which chi is going to standard model. Okay, this is very simple. Rate at which chi is going to standard model. So you can think of like chi, sm, sm, and you can think of like sm, chi, and not using any model, so you can think of it as a effective kind of model. Okay, now let's try to bring the cross sections. If we are doing only like 2 to 2, we can easily take the cross section into the picture, which is very convenient for us. So if you look at the definition of cross section, sigma, what is this? Is basically the rate per unit target particle, number of target per unit incoming flux, okay, multiplied by beam flux. Okay, this is the quantum mechanical definition of cross section, okay, which we always use in field theory also. So that means if I use this definition, I can find the rate in terms of cross section if I stick to this kind of processes, which is very simple. If you go to 2 to 3, 3 to 2, then it will be a bit slightly complicated. Then you have to use the more rigorous way. But for our job, it is actually good enough. So now I can find out rate for chi to sm as sigma chi to sm multiplied by, I'm interested in this guy, rate, chi multiplied by number of target multiplied by beam flux. Okay, so this guy should be n chi v, because one chi is coming and hitting another chi. So number of target is number density of chi multiplied by the volume. That give me how many number of chi is there. So that is my number of target multiplied by beam flux. Okay, so that beam flux is n chi multiplied by velocity. It gives you number of particle per unit area per unit time. Okay, this is number density. This is the relative velocity between two chi's. Okay, very simple. So now I can write down. Now I have to find out this guy also. So this is for this guy. Now this is for this guy. Now when these processes are happening, standard model guys are always in equilibrium. Okay, so that means this rate I can write as rate in equilibrium for sm to chi. Now we know that if the processes are in equilibrium, there's no difference between forward and backward. There's no direction of time. So I can write this thing exactly as rate equilibrium chi sm. Okay, so what I will do, I'll just write the same thing. Only difference I'll do is that instead of n chi, I'll just write n chi equilibrium. N chi equilibrium, because that is the only thing which is going to change when I go from equilibrium to non-equilibrium. Okay, so that means I can write down my Boltzmann equation now as dn chi dt is equal to, and this dn chi I can write as small n chi multiplied by volume dt is equal to sigma. So when I write sigma, I mean sigma chi to SMSM. So I'll not write the whole thing because to save space. And then multiplied by relative velocity and then n square, because this will give me an equilibrium square, equilibrium chi minus, and that this one will give me n chi square multiplied by volume, right? And the volume in the FLRW is basically a cube V naught. V naught is the co-moving volume, and A is the scale factor. So V naught remains constant, only A increases, that actually increases the size of the universe. So if I use it here, I can find out that since V naught is actually a constant, it will just factor out and it will actually cancel from all sides. And if I differentiate this, I get two terms. One is for the differentiation of A cube, and the other is the differentiation for N. Okay, so this will give me the equation, the final equation, dn chi by dt plus 3h n chi is equal to sigma v relative and equilibrium. I can write n chi squared, put a minus sign, minus n equilibrium square. Okay, so this is the familiar equation for the Boltzmann equation for dark matter for 2 to 2 processes. Okay, and typically we try to do a thermal average in the sense that not all dark matter particles have the same velocity, because dark matter particles or Stern model particles, they are in equilibrium, so they follow a distribution. So some guys have, most of the guys have the mean velocity, very few guys will have a very high velocity, very few guys will have a low velocity. So you want to integrate over all the things, so that is more appropriate. So you will write it like this. Okay. Now it turns out that it is more convenient to write down this equation because you get two terms here. So you would like to write down things in terms of co-moving coordinates. So in terms of co-moving number density, you write something called y, which is n by s. Okay, s is the entropy density, so this is 2 pi square by 45 z star s t cube. So it goes as t cube, and also goes as t cube when it is in equilibrium. So y is actually a constant. Okay, more or less. So if you want to write it like this, you also keep in mind that SA cube is equal to constant, because entropy per co-moving volume in the universe is constant because it is a adiabatic expansion, it's a closed system. So this is always constant, entropy density multiplied by volume. So this actually gives you, so if you use this and if you use this equation, you can write this equation in terms of y, which is dy by dt. And you can find that dy by dt will, let me skip some steps, those will be there in my notes anyway. So you can write down dy by dt as minus sigma v relative s y square minus y equilibrium square. Okay. You can also get rid of this time, because time, if you want to integrate this in terms of time, time is a large number from 0 to recombination. So you have to deal with these big numbers. So usually people try to replace this with something like a dimensionless number, which is called x, which is m chi divided by temperature. You can also do that because you know the time and temperature relation, because all these things are happening in a radiation dominated universe, and you know the time temperature relation. So you can always make a change of variable from time to temperature, and you can write down d by dt is actually x h d by dx, and h is your Hubble constant, which is 1.66 z star half d square by m Planck. Okay, it's coming from the Friedmann equation. So this will help you to write down this whole equation as dy by dx is equal to minus sigma v sx by h m y square minus y equilibrium square. Hm is h multiplied by x square. Okay, and you can see that this equation looks much more simpler compared to this equation, because you don't have to keep track of this. It's already included there. Okay, so now one can solve this equation if you know sigma v. Okay, and you can actually do some kind of approximation if you want to solve it analytically. So let's say after freeze out, you want to find out after freeze out After freeze out, you can actually ignore this part, y equilibrium, you can take it to be 0, for the reason I mentioned earlier, that equilibrium distributions become very, very small at, if you go to this one, it becomes very small. Okay, so you can ignore the equilibrium part. And then you can find out dy by dx is just equal to sigma v sx by hm y square. So you can actually integrate it now. If you integrate it, you will find yxf to y infinity dy by y square is equal to minus sigma v hm xf to infinity sx dx. Okay, and this quantity, if you find out, because you know s as a function of temperature from there, and that you can write in terms of x, you can actually calculate this. It will come out to be a constant. So what ultimately comes out is that your if you integrate this, you will get y infinity plus y xf is equal to minus sigma v, some constant. Okay, so you can, since y at xf will be more compared to y at late time, so 1 by x y is at xf will be small compared to this guy. So if we ignore this, all these are approximations, of course, it will not give you the exact result, but it is good for to understand something analytically, to know the picture. So this actually tells you that y infinity is proportional to some constant divided by sigma v. So it tells you that dark matter abundance at late time will be inversely proportional to the rate at which it is actually annihilating into standard model particles, which is very much physically intuitive, because if it is more annihilating itself into standard model, that means it is destructing itself more. So if more it destructs, less will be its abundance. Okay, so if you want to plot it by solving more rigorously, what you will find that at very small x, that means very high temperature, it is already in equilibrium. So it will be a flat line because it is n by s, both goes as t cube. And at some point, it will start falling like this because you have this e to the power minus m by t. And if you do not make it freeze out, it will just go down to 0. But you make it freeze out at some point. So this is the point at which it freezes out. You can say that this is the number density sigma v, which is the rate of interaction, becomes smaller compared to the Hubble at this point, so that it actually, the rate at which two particles coming and forming something else is less compared to the rate at which two particles are going away because of the expansion of the universe, because of Hubble. Okay, so this is the point, and after that point, it actually remains like this. So after that point, it still falls because chi can still go into the standard model, but standard model cannot go to chi because they do not have enough kinetic energy, because standard model particles have less mass compared to dark matter. So they rely only on thermal energies to go into dark matter, but the temperature has already fallen below the mass of dark matter, because that's why you see the suppression. So they can no longer go into standard model. So that's why you see a small fall here, but eventually it remains, so it's actually frozen out. Okay, and more the cross section, so the cross section increases in this direction. More the cross section, less will be the dark matter final abundance. Okay, so this is the typical WIMP miracle. I'm running out of time. So, and the interesting thing about WIMP miracle is that if you rotate this diagram, for example, chi to standard model, SM, chi, the same thing can give you indirect detection. In this direction, if you look at in this direction, it can give you direct detection. A chi can come from somewhere, scatter off a nucleon in our detector, again go to chi, and you measure the recoil that you get in your nucleon or nucleus in your detector. That gives an estimate of the dark matter mass and its interaction rate with the standard model guys. Okay, and you can also, if you go in this direction, it's collider. The proton comes together, produce chi. and that will be missing energy. So it's very popular in that sense because it is not only gives you what dark matter is or dark matter abundance, you can actually verify it experimentally very easily because it has some sizable interactions which can be probed. Okay. But unfortunately, we had not seen dark matter in direct detection experiments for a long time. And that actually has led to some kind of paradigm shift because people have started asking questions that are we looking at the wrong picture? Oh yeah, it will fall because you have this, no? Because the rate at which two chi's will come together and form SMSM, that is falling compared to the rate at which two chi's are going away from each other because of the Hubble. Yeah, but this picture is average in the FLRW universe. There is no galaxy, there is no perturbation, there is nothing. So on average, dark matter. So if this condition actually tells you that on average in the universe, dark matter interactions coming together forming SMSM has completely stopped. But if you are in locally, for example, the indirect detection, if this has stopped, why people look for gamma rays coming from dark matter annihilation in the sky? Because it is a local. So locally, what will happen is that inside, at the core of the galaxy, you have so much of gravitational potential. The dark matter has more velocities, more energies compared to on the average. On the average, it is almost zero energy. It has only mass. It's not moving. But if you go to the galaxy or clusters, dark matter is also moving because it has velocities. It's allowed by the gravitational potential. So then it can come actually. So this is for an FLRW, pure FLRW universe. Yeah. Okay. So since we had not seen freeze out or WIMP, that actually motivated people to look at something called FIMP. It is completely opposite. That means it is not there in the universe earlier, but it is produced from what we have in the universe by some kind of decay or scattering. Okay, so that means the rate of chi with SM is always less compared to Hubble, always. So it never comes into equilibrium in the universe. Okay, so how to produce it? So again, you do the same thing. You find out dn chi by dt is equal to, let's say I talk about a particle A which goes into chi chi. This A can be the standard model Higgs, it can be W boson, G boson, I don't care. Let's say it's A. And this I will try to find out. So it is going to 2 chi's. So that means I will write 2. Then the rate at A goes to chi chi multiplied by number of A minus rate at which chi chi is going to A. So this is basically the rate, this whole thing is basically the rate at which A is going to chi chi, which is actually proportional to the decay width, because decay width is actually probability per unit time that it is actually decaying into chi chi. 2 is coming because A is going to 2 chi's, okay? That is 2. And it is proportional to number density, number of A. More the number of A, more chi you produce, right? That's the idea. And again, I can hear what happens that unlike in the WIM case, in the WIM case, chi was in equilibrium, so it has a large number density to begin with. But here, chi is never in equilibrium, so chi initial abundance is almost 0. And this rate will depend upon what number density or number of chi you have. So chi number is very, very small, negligible, so you can actually throw it away. You don't have to worry about it. You just worry about this term. Okay? So if you solve it, so again, you can write down this equation as in terms of number density, this is number, you can write out in terms of number density, plus 3h n chi is equal to 2. Again, I will do a thermal average, chi chi n A. Okay? Once again, I can go from the number density to the co-moving number density, and this equation will become dy chi dx is equal to 2 x h y a. Okay, And this is a thermal average of the decay width. So if you want to calculate it, this is actually you have to integrate over the momentum of the uh, A particle, mother particle, and dqp e to the power minus Ea by T. I'm assuming a Maxwell-Boltzmann distribution for the particle A. I assume that the particle A is in the bath. Okay, that is simple because then I don't have to solve the equation for A. I just solve the equation for chi. If I do not know the distribution of A, then I have to solve two equations, one for A, one for chi. So the problem becomes a bit more complicated. So, and this gamma A is the Lorentz factor for the chi, because I'm assuming that A is not at rest, but with some kind of, because A has a distribution, so it is not necessarily at rest. So this is just E by M, okay, for A. So this, if you write all these things, it will just be very simple. It comes in terms of modified Bessel functions of the second kind and the usual decay width at rest. Okay, so if you solve it numerically, then you will get abundance of these guys. I will skip some of the analytical things, but essentially what it comes out is that omega of chi comes out to be m chi y chi s at t0 divided by rho c0 is actually some constant which we don't care, m chi a going to chi chi m a square. Okay, so basically you have to integrate this equation, okay, which I'm not integrating here because of the lack of time, but you can look at my notes which will have the steps. But to get the more exact results, you would like to numerically integrate it in some codes, and that will also give you more exact results. But now if you want to look at, we just want to look at what physics decides the abundance of these guys. So here you can see that if you want to plot the abundance as a function of x, you will find a completely opposite picture compared to that plot. You just invert that plot. What is happening here? So if you find out y chi in the film case, we have already assumed that chi is very small in the early universe. So that means you don't start here. You start here. Okay, it grows. It grows. How it grows? You see the expression, final expression. You see that it grows. So if you have a large probability of A going to chi, more is the decay width of A going to chi, more is the dark matter final abundance. That is the dark matter final abundance. So it will grow like this. It will grow like this. So in this direction, your gamma A going to chi chi is increasing. So it is completely opposite. The interaction of chi with the standard model guy, or A, if it is more, you produce more dark matter, provided you always stay in the film ballpark. That means the rate of interaction is always below Hubble. You cannot increase it beyond the film ballpark. That will take you to the WIM ballpark, where your analysis will be completely different. Okay, so but there, more rate of interaction, less is the abundance. Here, more is more the rate of interaction, more is the abundance, as long as you are in the film ballpark. So this is good enough for the dark matter part. You can reproduce what is the observed dark matter abundance. But the problem is that if you think about this A chi chi, so if you think about what kind of coupling you should have, you'll find that this coupling will be of the order of 10 to the power minus maybe 10 or so. Okay, it's very small, so that this rate of interaction is always below Hubble in the early universe. Okay, so it's very difficult to probe this kind of scenarios. Okay, if dark matter is long-lived, it can decay into standard model guys on a cosmological scale. So you can probably see those decays, but you cannot. There's no hope of seeing in the ray detection experiments. In the ray detection, if it decays into, say, some kind of gamma rays or some kind of neutrinos, you can actually see it. And if the dark sector is richer compared to just having one particle like chi, then its companion particles can be produced in the experiments if it has large interaction, and they can be long-lived because they will interact with dark matter with a smaller coupling. So there are works people have done where they have discussed like how these companion particles can be produced in the colliders, and they can decay with a long lifetime into dark matter. So that will give you some kind of displaced vertex or long tracks, or some kind of missing energies. Okay, so finally, so these are the two well-known mechanisms, but I wanted to discuss quickly one another mechanism which is very common or very popular nowadays, and it is related to axions. I'll not talk about axions, but I'll talk about one of the mechanisms to get axion dark matter. And it is not necessarily that you do it only for axion. You can do it for any light scalar. Okay, for your, let's say your dark matter is very, very small mass. Okay, say, so this is my number 3. So let's say your dark matter mass is MdM. It's very, very small compared to even electron volt. Now, as I mentioned already about the neutrinos, this obviously tells you that it cannot be fermion because it is ruled out from the termine gun bound, but it can be scalar. Nothing prevents you from having a scalar dark matter having very, very small mass, like less than electron volt. Now, what happens for this kind of dark matter? You know that 26% of the present energy density is this kind of dark matter, and they are cold. So you can find out the number density of dark matter by observe by mass. So if mass is very small, you get a very, very large number density. So the occupation number of dark matter is so huge. Essentially, there is no gap between two dark matter particles in any way. So you can think of it as a classical field. Okay, so that actually gives you a very different type of production mechanism. There are many ways. So the most popular one is something called misalignment mechanism, which you can apply for axions also. So what happens is there, for example, you have a scalar field, you write down the Lagrangian, real scalar field. Okay, so the Lagrangian, you can find out the, you can say that if you say the potential is like this, let's say V phi is just m square phi square. Okay. So since we are treating dark matter as a field, not as a particle, so I just have to worry about how this field evolves in cosmology. That's what I want to do about. Okay, I'm not really interested in the particle picture which we deal with in terms of cross sections or decay widths. I don't have to worry about those things. So here, now I have to find out the equation of motion for this field in a FLRW universe. So for that, I can find out, for example, if I find out energy momentum tensor for this field, it will be del mu phi minus eta mu nu Lagrangian. Okay, and I also know how to write down p mu nu. So this is diagonal rho minus p minus p minus p, and this, if I find out, I will find, because I will want to compare this with this. Okay, I can find out what this quantity is in terms of this. So if I assume that my phi is only a dynamical field in terms of time, because I'm talking about FLRW universe. So phi cannot depend upon space, it will depend only upon time. So then this becomes very, very simple. So I can find that my rho phi is phi dot square by 2 plus V phi, and pressure P phi is phi dot square by 2 minus V phi. So if I find out the equation of state omega, which is P by rho, that is basically phi dot square by 2 minus V phi, and phi dot square by 2 plus V phi. Okay. Now what happens if you want to find out the equation of state? So for example, if you use the continuity equation in an FLRW universe, which is del rho by del t plus 3h rho plus p is equal to 0. Since you know the expressions for rho and p, you can put it here, and it will give you the equation for phi, which is phi double dot plus 3h phi dot plus v prime phi. And this I can write as m square phi for this potential if I have taken p phi to be m square phi square by 2. Okay, so what this equation reminds you, this is just the damped simple harmonic oscillator. Very simple, damped pendulum. Okay, we already have learned it in school, so we know how to solve this equation. Okay, it's very simple. So what will happen? So if you start at early times, you know that your Hubble, because Hubble grows as t square, so Hubble is very, very large at very large temperature. So at very early time, you can see initially H is more compared to M. So if H is more compared to M, so this is a friction term. So the friction is more compared to this is the oscillation term. So that means if you look at the potential, if the field is here, it will stay there because it's too much of friction. It actually prevents it from coming down to the ground state. Okay, you start wherever you want. Okay, that's an initial condition which you are choosing, of course, but it will stay there. And later when H becomes less, because H is going down because it is t squared, T is falling, so H is going down. M is fixed, of course. So at some point H will fall below M, and then it will actually oscillate. It'll come down, it'll come here, and it'll keep oscillating. Okay, so if it does that, you can find out the oscillation time when this happens. So H t oscillation is equal to M, and this oscillation should happen before the matter radiation equality, because then only it can be dark matter, right? So that actually puts a constraint that this mass, if his mass is more than 10 to the power minus 28 electron volt, because Hubble at matter radiation equality is of the order of 10 to the power minus 28 electron volt. Okay, because matter radiation equality happens when dark matter actually takes over radiation. It's not the baryon, because baryon is already small compared to dark matter, right? So any scalar having mass more than 10 to the power minus 28 can be a dark matter candidate. So how to calculate the final abundance of dark matter? So if you calculate the oscillation time, so the oscillation time one actually calculate, because you have a 3 factor there. So 3h is equal to m, and that gives you 3 by 2 t oscillation, because Hubble is 1 by 2t in radiation dominated universe. So this gives you m. So this you can use depending on the mass of the scalar. You can find out at what time it starts oscillating. More is the mass. If mass is more, then the oscillations will be earlier. Okay, so if you solve this equation, so you can find out what is your rho at t oscillation, and this is basically m square by 2 time average of this phi square, and this is nothing but your m n t oscillation. Okay, we are still assuming that at oscillation we are still assuming phi dot almost equal to 0. It just starts oscillating, so phi dot I am still taking as 0. And if you solve it numerically, so this is your density at t oscillations, you can find out the density at t0, and this will be just the scale factor a oscillation by a t0 whole cube. And how do you know that it behaves like a matter? We solve these equations, and we find that if we plot omega, which is the density of, which is the equation of state parameter, it starts with -1. Why it starts with -1? We can see that omega, because phi dot is 0, so this is minus v phi by plus v phi, so it starts with -1. So it's almost like a dark energy. So it starts like this, but when it starts oscillating, h is falling, so it will actually looks like this. So it will start oscillating about 0, and 0 is the equation of state for dark matter. So if you do a time average, you will find that this is actually behaving like a dark matter. And if you solve for the phi by this damped harmonic oscillator, you will find that it starts with some value. That's why I said you start with wherever you want. This is v phi. So it has an initial condition problem, because it is up to me where I choose it to be. So you start with some reasonable value, and then it will actually start oscillating. So this is say m1, You say M2, M1 is more than M2. So this is like a scalar field which is oscillating about 0 and behaving like a dark matter. And this is very cold. And this is not, it is kind of non-intuitive in the sense that we always think that a particle which is so light should always be relativistic, but this is not. Because it is, you are not producing this particle from decay or scattering. So you cannot do the FIMP mechanism for this particle. Why? Because these particles will then be very relativistic all the time, because you are producing, for example, you are producing this guy from Higgs decay. Higgs is 125. This is say 10 to the minus 20 electron volt. It will always remain relativistic for a long time. So you don't want to do that. So you're just doing it like a coherent oscillation of a scalar field. You are not bringing the particle picture into the here, because it is not even needed, because it's like continuous field. Okay, so this is very popular and people are using it for the axions. And axions, of course, what will change for the axion is the shape of the potential. You know that axion has a cosine potential which comes from the QCD, and axion, if you apply this, you find that the correct dark matter can be obtained for axion decay constant with some particular value. And those values are interesting because you can probe those axions in experiments, because axions has a very interesting term in the Lagrangian, which is A by F, F tilde. Okay, and if you remember electromagnetism, this is just E dot B. That means if you have an axion in the presence of magnetic field, it will convert into a photon, or vice versa. So that's why people are building very low cost experiments using cavities and all these things, which are looking for axions in the so these are some kind of hot topics nowadays. So that's why I wanted to give a very small overview. Of course, it is very limited, but I hope it will be interesting. There are many other dark matter candidates which I mentioned, maybe just 1 or 2 minutes. I mentioned about right-handed neutrinos, nu R. I said that you introduce 3 of them in the type 1 seesaw. One of them can be dark matter. How to produce those dark matter? One very straightforward is L bar H tilde nu R. You make this Yukawa less than say 10 to the power minus 9 or minus 10. What it will do? It will do the M lightest very, very small. Let's say maybe 10 to the power minus 10 or whatever. Very, very small, let's say, compared to M solar. Okay, but that is fine because we want to produce only 2 masses. That is okay with the data. But if you do it, what will happen? That Higgs boson can decay into right-handed neutrino, just like a FIMP mechanism. You cannot do WIMP here. The problem is that if you do WIMP, you need large Yukawa. If you have large Yukawa, dark matter can always decay into the standard model guys. And also, even if you kinematically suppress it, what will happen is that it will be difficult to satisfy the seesaw relation to get neutrino mass. You'll get if you take it large, if you keep nu r in the WIMP ballpark, you will get a very large neutrino mass, which is not correct. Okay, you can have it like a FIMP. As I mentioned yesterday, you can also produce it from oscillation from nu to say, okay, light to heavy. There are 2 popular mechanisms. One is called Dodelson withdrawal, which does not require any resonant enhancement. The other is called C-Fuller. So C-Fuller uses that MSW resonance I talked about. It has a medium, it has some kind of primordial asymmetry, and that actually, because our ordinary matter has electron, no positron. So if you create a primordial asymmetry in the early universe also by some initial condition, then you get a resonant enhancement for production of right-handed neutrino from the light neutrino oscillations. Okay, so these are typically for the keV mass range. If for FIMP, you can go to MEV, GeV, whatever you like, no problem. Any mass range. As long as your Yukawa is small, it's fine. But this is, you have to oscillate. So oscillation from light neutrinos. So you cannot make it very large because then the overlap of the wave functions will be very small, right? So, and these kind of things you can have, if you have nu R, you can always have, because they mix with the ordinary neutrinos, so you can have an electron, W, there's a nu L, you can have a photon. Okay, so these are very nice signatures, because in this model, type 1 CISO model, NUR is not perfectly stable because there's no symmetry. You are only making it long-lived, so you can have this kind of decays. So what, for example, this guy will give a gamma, which is having energy exactly as the mass of dark matter divided by 2, because neutrino is massless. Okay, so this will give you monochromatic photon lines. Okay, and this model was very popular when people saw this 3.55 keV line in the X-ray spectrum, but that is not there anymore. Uh, I wanted to talk about scotogenic, but I don't have time. But we can discuss. It's also there in the notes, so I'll probably stop here. Thank you.
Any question? Nope. The question was
Yeah.
if you have any favorite production.
Well, I mean, yeah,
mechanism.
that's a time-changing. Of course, WIMP is always the favorite because it's minimal and it's. But now, I mean, I also like this kind of scenarios because it offers new ways of probing. So, to answer this exactly, like it actually changes with time because our field is also like that, right? So, WIMP has always been a favorite, but now I am also looking at some of the mechanism which gives you some complementary detection probes. Yeah.
Okay. No. Okay, Leandro.
Can you repeat what you said in the last thing you told? Because I didn't quite understand why you said the right-hand neutrinos cannot be a WIMP, but it
Oh,
can
it
be a
cannot be WIMP.
FIMP.
Okay, good. To have it as a WIMP, you need this Yukawa to be large, right? Because you want to produce it in thermal equilibrium in the early universe. So this Y will be like order 1.
Okay.
If Y is order 1, if because the neutrinos are very light, so this will decay very fast. You can prevent it kinematically. Let's say, okay, Higgs and L is, you can say Higgs plus L is large compared to nu R, but then also you can go to 3-body decay. This can go to 3 neutrinos, like we heard in the talk yesterday in the afternoon. So it will decay very fast. So it will not be long-lived.
All right.
So you need to tune the Yukawas.
No, that's it. Thanks.
Any more question? Okay, Lucia.
I read some papers about the SIMS. Could you please explain a little bit more?
About what?
SIMS.
SIMP.
Yeah.
SIMP.
Like a candidate of dark matter also, but I'm not involved in that kind of mechanism. So please explain a little
Okay,
bit
so
more about
SIMP,
it.
you're talking about probably strongly interacting dark matter. So it's called strongly interacting dark matter. So what happens is that so SIMP is interesting in some sense because it solves some other problems. So that's why people have proposed it. SIMP. So from all the evidences, I know that dark matter interactions with the standard model is gravitational, plus maybe some small interactions of the order of electroweak or smaller. But we do not know that what dark matter, for example, you have chi. What chi interacts with itself? Is it gravity? It is something more. This interaction can be much bigger compared to dark matter standard model interactions. Okay, so SIMP is proposed for to have some large interaction among the dark sector. Why do you want to do that? Why do you want to make it complicated? WIMP is so simple. Motivation is that what it solves something called the small scale structure problems of CDM. So what happens is that if dark matter is actually interacting with a large rate among itself, there will be more dissipation. So what cold dark matter does, if you look at the profile, so it gives you something like this. You don't observe it exactly in the astrophysical observation. So what people try to do is that they actually try to introduce some large interaction among dark sector. So it makes the dark matter profile. So this is like a dark matter profile as a function of R. So it makes it like this, which is observed because you have more dissipation now. It is losing energy, okay? Because your dark matter is like, if it is interacting strongly, there's a heat within the dark sector, right? Because it is interacting so much. So it will try to make the dark matter particle go away slightly, okay? So you get this profile which is like this. So this is called the core versus cost problem. So there are motivations. There's one more motivation called the missing satellite problem, because cold dark matter is so cold and non-relativistic, it produces more structures than you actually experimentally observe it. So if you introduce this, it actually solves that problem. So this dark matter behaves exactly like cold dark matter on very large scales, but if you go to small scales, it gives you some deviations, which actually you want because of the problems at the small scale structures. So that's why people have proposed it. Yeah.
At the time we want to detect it.
You want to detect it? Its detection will be exactly same as because this is the interaction among the dark sector. It cannot have such strong interaction with standard model. That is not allowed. So that's why the detection prospects will depend upon whether the SM couples to chi like a WIMP or a FEAM or whatever you want. That's not a problem. But all they do is that they have a large interaction among themselves, which has some advantages.
So the difference is it's when you describe the interaction of the model itself, not with the standard model, right?
Not standard model, yes.
Okay,
So,
so
for example, you have some kind of SUN.
Okay. So it's a strong interaction, just like QCD.
You can have a QCD also. There are models. People have taken like a QCD type of model, dark QCD, where you have a confining sector. But those models are, I mean, like a complicated ones. You can have a very simple kind of interaction. You just introduce a scalar field, and you have a dark matter like a fermion. So chi and chi interacts just with a scalar field. That is also equally good. It also solves these problems. It's much simpler.
I see. Thank you. More questions?
I'm not sure if I get that right, but you did you say that dark matter don't collide with each other? They don't interact with each other like physically?
That's a very good point. Yes, I mentioned this. For example, bullet cluster tells you that dark matter should be collisionless. Okay, so now when you introduce this thing, you have to make sure that at the scale of clusters, because the bullet cluster, it should obey because bullet cluster gives you an upper bound on dark matter self interactions, because it has seen that dark matter just goes through each other without even noticing each other. So it gives an upper bound. So you have to satisfy that upper bound at the cluster scales. You remember, I mean, I should also point out that these interactions are scale dependent. They can, because it can be velocity dependent, if you have some p wave separation. So you can always cook up some models. That's why these SUN models are more popular, because they actually give you exactly what you want. Here you have to be a bit careful about the couplings. So you have to get that large interactions only at some small scales, not at the cluster scale. Cluster scale, you have to obey that bound. So this is something called diversity problem. So you have to make your model in such a way that it agrees with cold dark matter on large scales, but give you something different at small scales. Yes.
Thank you very much.
Now I'm kind of confused. What are you calling small scales? Kind of planets, stars,
Not planet. I mean, it's like
galaxies?
maybe kiloparsec. Yeah, galaxy.
Okay.
Yeah.
So you should have kind of in clusters. It should be different behavior.
Yeah.
Yeah, it's a tough problem to solve, right?
Yes.
Yeah. Okay. Any more question? So let's thank Professor again.
So for those who are hearing, still